In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion.
All right, hello and welcome everyone to Aether Roundtable number 66. 66 weeks in a row, boys. Tonight we're going to be talking about sky optics, maps, and maybe we'll dabble a little bit in the ancient technology of building a canal. See how the lads did it back in the day. Shane, whenever you are ready, sir, to take it away.
Nice. Thank you, Alan. Thanks, everyone. So yeah, we got sky optics, maps, and
Oh,
canals,
sorry, real quick before you begin. This is a super open panel discussion or whatever. So if anyone has any questions, comments, needs clarification, now would be a fantastic time to bring those questions forward so that they can get answered and it'll be beneficial for everyone. So no such thing as a stupid question. And if there is, you'll know because you'll get banned immediately. All right. Continue.
Or we'll make fun of you. One of those two things.
one of those two things.
Before you arrived, we were talking about the Battle of the Maps thing where they were using different maps to use propaganda. Are you going to cover any of that in the presentation?
Nope, but it's always worth mentioning right at the start. We are going to go over some cosmography and enhanced cartographic projections. So yeah, that one should be aptly titled How to Lie with Maps, right? Similar to How to Lie with Statistics, right? Things that are actual tools you can just use to dissuade, persuade, or do whatever you want with if you know how to control the data and, of course, know how to use your tool. As what not to do then would be to not know how to use your tool and get cut by your double-bladed weapon, right? So, for example, if you don't know how to use an azimuthal equidistant projection, you might think that maybe has been debunked recently, right? Just to say a couple things. Actually, that brings us to the start, right, of do you guys see that second slide? No, it looks like
we're looking at the thumbnail, brother dog.
Still first slide. Okay.
Yep, there we go. We're on.
Go. Wow, that's a delay.
Oh, did you make your own no hypothy?
No. I just stole yours, which which you stole from us. So I mean, technically, it's just it's all the same.
Nice.
Well, I screenshotted the end. So I wanted to start with the null hypothesis because I think it's such a great way to frame it. And we're going to be concentrating, I think, mostly on this, at least for my part, right? So it starts with H0, right? Earth is planar. Measurements of curvature are dependent on the position of celestial bodies. We're going to provide evidence for that. We're going to try to disprove that, right? And the other one would be the Earth is globular and measurable curvature is thus independent of these celestial bodies. Now, that is the way we're going to frame this because we know overwhelmingly that we can provide heaps of evidence for this and zero pieces of evidence for this, no matter how hard we try, thus leading us to conclude that all measurements of curvature and sphericity come from model-dependent measurements of the sky taken off planar measurements and put into spherical coordinate systems, and we're going to provide evidence for that, right? So as we go into it real quick. Oh, man, it's really going slow because in my Canva, oh, you know what? I got to be in my Canva first.
Dude, did you have an audio track for the Indiana Jones switcheroo?
I did, but it doesn't.
Respect. We totally heard it and just got copyright struck by Universal.
No way.
I mean, it'll happen.
It wasn't even playing. That's fine.
It's all good. It's funny.
It got blocked out. Perfect.
There it is again. Yeah.
Yeah, don't worry. I muted it. Yeah.
What is happening with my Canva, dude?
Not looking good.
You got open.
None.
Here we go.
Anyway,
Here we go. We're back.
a good depiction of this geographic graticule, right, as we know it, portrayed simultaneously in our nice Mercator equirectangular depiction, as we're so used to seeing it, and our spherical orthographic projection, as people like to think as the world, right? These 2 points are synonymous. As this moves up and down, you can see the coordinates changing over here. Now, we're going to go through real quick what it's based on, which is just angles to the stars. You know what, man, this is whack. I think I got to change the presentation mode because it's so far behind.
Huh. There you go. Looks much smoother. Yeah, there you
All
go.
right.
Whatever
All
you did.
right. So that was weird. Oh, and I can't stop it. That's fine. So yeah, essentially it's based on our daily observations anywhere on Earth. The fact that you cannot see all of the sky, right? That you only see half of the sky signifies that you have a limit to the vision that you have, right? You cannot see all of the sky. Therefore, if the Earth is flat, there are parts of the sky you can't see. Your vision is limited. These are easily logical deductions, I think. And most people would agree with this. So if you could then portray it as like an upside down bowl over where you are, right? And then you have observations of things rising and setting as they come and go to and fro over your dome. Now, of course, to other people, they see a circulating celestial object differently. If you see it at your zenith, someone over here might see it rise. And, the globe model, of course, is based entirely on this mechanic. Here we have a nice observer on our flat plane. And we have, how's my audio? Did it drop off again? Yeah.
Nope, you're solid.
All
No,
right.
you're good.
So it's on observer on a flat plane, and he's observing the sun rising and setting. Now he's looking. This is east and west. It's flipped, but rising and setting. Now it goes for a different declination depending on the season, right? According to him in his little grid, the sun goes from the summer all the way down to here to winter, and then all the way back up here to summer. So high and local, or far down and low for this northern observer, right? So it varies by season. Now, based on this mechanic and this observation, the entire globe model is constructed. All right. Now, varying parts all over the Earth, you have this have different varying effects. You get this these observations over the flat Earth, when put in aggregate, could then be used to form what is the celestial sphere, which is just a combination of people's views of the heavens from all over the Earth. And from that, they compose a mathematical bottom, meaning the bottom half of the celestial sphere, through the negative fundamental plane, which is just a mathematical expression. It's an easy way to keep track of celestial objects that you can't see. You pretend they're beneath your feet. You calculate that circumference. And when they're actually circulating around you on the same circumference, you can predict accurately when they'll come back around. And that whole mechanic is exactly where the globe model comes from, where it's born, how all the observations of the sky match it, because that's what it's based on, right?
Would you say that a key element of this is dependent on interpreting the light coming from the sky as directly parallel rays that could only be deviated due to the contour of the Earth? Like the only reason you see anything do anything in the sky basically is because you're on a ball and you're at some angle to the sky.
Right. For the ball believer, they see that this deviation in sun angle actually means because, of course, the sun's rays are absolutely parallel and they're coming from such a far distance that actually what's happening is the angle of the Earth is tilting on its axis as it goes to and fro in its orbit around the Earth seasonally, so that the 23.4 degree tilt gets more parallel light rays, right? And that's the ridiculous explanation for this inclination in sun angle. Yeah,
So
it goes so far.
Okay, so if there was evidence for this dome of vision thing, you would see like a parallel light ray go across the sky in a way that it diverges and reconverges behind you then, like mechanistically.
Right. You would see sun rays converging in a counter convergence point, and known commonly as anti-crepuscular rays, right? That would be a benefit, sure. I mean, an aspect.
Have you ever seen an anti-crepuscular shadow?
No.
Do you want to?
Yes.
Give me a second, or keep going. But I'll bring it back up because what it lends to, right, is we have an optical mechanism for light bending completely around you, in the same respect that we've always heard the argument, oh, well, if I get my telescope and look horizontally on with respect to certain refractive conditions, I could see my own arse, as they say, right? Now, most people will not say that out loud because they want to maintain like the illusion that their position is falsifiable. But when pressed, ultimately any observation will be refracted up. So with any conditions invoked that to make it necessary to make it fit the ball. So you would have, so this is like a separate mechanism, right? So if we're talking refraction to bend light over a distance to wrap around a globe, right? You need a specific gradient, you need specific conditions. That gradient has to be maintained for however long the distance is, etc. Right? But here we're looking at a natural optical phenomenon where light rays, assumed parallel, are observed being bent around you 360 degrees in such a way that they diverge and converge behind you, or they diverge as they're coming towards you and then converge behind you. And like mechanistically, right, this is just purely an optical phenomenon, irrespective of refractive conditions or any other sort of mechanism that can affect light that requires like a density gradient to be supplemented to provide that mechanism.
No, I had a presentation called The Sun that would do that excellently, but yeah, no. Anti-crepuscular rays would be a perfect demonstration of how we exactly see those light rays doing that. And what the globe does is explain it away by saying, actually, that's just perspective, but in reality, it's totally doing this totally parallel light ray for everyone, even though no one can observe it and it's never been verified. It totally is. Trust me, bro.
Yep. Hey, real quick, I sent you a DM of that video. If you could pull it up real quick, we can look at the anti-crepuscular shadow and we can see the natural optical phenomenon that is actually wrapping sky phenomenon around your dome, literal and figuratively. Someone's hot micing. Who is it?
I can't even see Discord. There you go. Do this.
Oh, it's Andrew.
God damn it, Andrew. There we go. Perfect.
Nice. You just kind of skim through it. I think around 2 minutes or so, she shows the 180 degree difference on the shadows. So scroll forward a little bit. Yeah, that's not it either. Shoot, give me 1 second. I'll find the time. Oh, you found it. Yeah, right here. So she shows the looking out horizontally and then 180 degrees behind her, and the shadow cast by the cloud, completely starts to diverge and then reconverge around her 180 degrees behind her.
Cool. Yeah, perfect.
So this is an optical effect. It's not due to refraction or anything like that. This is just purely optics, man. This is light being bent around you so that and then like how you perceive it, like through your eyes. That's the mechanism.
Human perception. Yeah.
Yep. Yeah, exactly.
Excellent. Yeah, that's a really good visual observation. Let's see. I think I had a video about the ecliptic real quick. That's because it's super relevant for how we observe a half dome above us and what the tilt in that dome respect to a third-party orthographic view of the sun would look like, and then all the things they've concluded from there. And I think it's like 3 minutes. So it does have sound. You good? You good with sound? Can you hear that?
Absolutely.
Yeah.
Right, we talk about the sun's apparent migration from tropic to tropic and what it looks like to us. Now, what causes this is if you look at the flat Earth dome model here, right, you can see that the sun is on a slight tilt above the plane, right? It's not perfectly level on the slight tilt. It's about a 5-degree inclination. Now, the moon is on a similar inclination, but not the same. And the difference in those inclinations between eclipse cycles is what makes them miss most times when they intersect and not actually connect for a so-called eclipse, right? So
those two things are definitely present. The one from the sun, though, is what creates what we know as the ecliptic, right? So the sun's band is what we're looking at in each observer. So from here, you can see the sun travels from about here to about here. That's the 23.5 degrees that we're talking about in the ecliptic. If we get a different angle on it, we can see the analemma begin to form in the person's perspective, right? Because each person
Analemma,
would see the
not
in a
enema,
different position
analemma.
here. So that's where the sun is, and that's where the sun appears to be. So the migration of the sun annually is what we're calling the ecliptic. So this band, you see this band right here, the sun travels from this band depending on the time of the year, south of north, south of east rather, and set south of west. So it's rise south of east, set south of west. There we go. And again, depending on the season, it does the opposite. Rise north of east, set south of west. Okay, now that ecliptic band in each observer is what is making this possible. Again, right? This is the band. And this is again caused by the true path of the sun doing this. Right? As its migration, it goes up and down, it changes height, and it gets a little bit lower depending on the season, right? So if we looked at it from the top, you would be able to tell it just goes out and in, and out and in. And that's what we see on most of our simulations and most of our depictions when we're talking about it. This is what it shows you. But what it's actually doing in 3D is changing heights, right? That's all it's doing. That's what creates more and less light. If you look at it down, you can see that as it gets lower and out to the corner, it creates more and less light. But perfect. So all that just to say that that's how you would depict the sky above us, and that's how we're going to mathematically quantify it. And then from that point, that's how we're going to create the globe. Like 1, 2, 3. It's going to be super simple. So here's another depiction of this flat observer on a flat plane and observing rising and setting motions of celestial bodies, right? So it rises, it goes in this arc, it goes to its zenith, it sets, right? That's what everyone sees. That's what every object does. So if you were to describe that mathematically, right, you would start with a hemisphere and you'd use a spherical coordinate system because it would be absolutely identical to the hemispherical, except for one key aspect, and that there's this fundamental plane through the middle, and values below the plane are negative and above it are positive. And in that way, you use exactly the same spherical coordinate system to describe positions of celestial bodies relative to you, or relative to a geocentric observer, right? That's how all ephemeruses are. That's how all ephemeruses are geocentric, right? And they're all described by this. Things arise with an elevation angle, they make an arc, and they set. So that's what it's used, right? And again, the only difference between is the fundamental plane has positive X and Y directions. That's it. That you apply a sign to things below you. And again, when you can't see the sun, say when it sets, if you pretend that it's beneath your feet, you can mathematically describe it in a way that you can predict when the sunrise will be, right? Based on the circumference of a presumed orbital body. So as the sun orbits or goes around flat Earth up here, it rises and sets for different observers. And if you use this circumference to calculate when it will rise and set, it'll always be right. So, that circumference can be this. Same over here to describe a non-existent mathematically fictitious bottom half, the same way as you can to describe it a circumference as it circles above the flat Earth. So again, the fundamental plane is the only thing that divides it. It's a reference that divides the sphere or celestial sphere into two hemispheres. It's also a thing you need before you start taking measurements. One of the most common coordinate systems to take measurements in is the alt-az grid, and that just establishes basically your horizon, which again means you have a fundamental plane dividing it into two hemispheres, and from that base horizon fundamental plane, you make elevation measurements of the celestial bodies, right? So it's very basic.
So when we're looking at the fundamental plane, can you go back a slide? When you say they're taking elevation angles to a star and whatnot, so all they're doing is this observer would be in the center there of that XYZ coordinate system. You'd be looking out at per se a 45-degree angle, and then you're what? You're just going to start doing cosines to a star, and then following that distance.
Yep. And then this distance right here, right?
And then so you traverse that terrestrial distance, and then you're underneath a star. Now what? What do we?
Well, then you got to take a zenith measurement, right, to that star to make sure you're there, and then you got to line it up with your tool, but then you can't quite get it in the center. So then what do you do? What's a man to do, man?
What's a man to do when he follows the law of cosines, but he can't complete the triangle?
I think you just start making shit up.
Okay. So they have their 90-degree triangle expectation for a distance. They traverse the land. They get at the expected location where they would be directly under the star. They look up, take a zenny measurement, and they find that the star is not in the center of their telly.
Yep. So far, 100%.
Every time.
Let's go get Captain Cooked.
Now, again, this is the basis of the globe model. This relationship that you can do this and that this is right is like the backbone and the infrastructure for the globe model. So when they get there and it's off, the whole thing, should be reconsidered instead.
Yeah, I want to add something to this, right? So all these positions of the stars and how you can cosine to them and traverse the land and go and check and all of this was provided in the Nautical Almanac, which takes a snapshot of the stars on the vernal equinox, and serves as the reference point for all of navigation. And the distances to the stars are all assumed to be the same at your limit of vision. So it doesn't matter how far they say the sun or planets or Saturn is or whatever. It can all be considered literally at the rim of that dome in an equidistant web as it sets into the horizon for your field of vision, like as that dome goes down to meet the ground. And so anyway, they have this reference, right? And they go up and they start looking at the stars and they find that they're off. So they started saying that the reason that they're off was actually because of the shape of the ground. And that's where the reference ellipsoid comes from.
Yep.
Like those deviations from the expected perfect location. Now, earlier we were talking about how the model is built upon the assumption of parallel light rays coming directly in. Well, if you're making a triangle and you're assuming parallel light rays and you go and take your zenith measurement, you would expect that starlight to come right into your telescope and be directly in the center. But what they found is that it never is. And then so after they came up with this ad hoc explanation that the reason must be that the ground is curved, they started doing experiments in the 1850s where they would introduce a medium to the telescope in which they were viewing the star from to determine whether or not the difference between the apparent position and if the apparent position would change due to Earth's motion. And what they found was that there's no change in the apparent location of the star, which means that when these lads get together, they cosine out a star, traverse the land, and look up, they're never, ever, ever going to see a star in the center of their telescope because the starlight already comes in at an angle that they're all whatever they are in the sky, they're always moving. And they already come in at an angle. So there is no idealized location for these things. This is all in reference to what it would have to be to maintain accuracy of the coordinate system for you to have a reference to. Like, how all of our units of all of our units of measurement are defined by some other naturally occurring phenomenon, which can be referenced against. For example, for a meter, they'll use the wavelength of gamma radiation, I think it is, or some specific type of cesium radiation, I forget, but they have like a physical thing to compare it to, right? So there has to be this reference, and this model that they've constructed is actually like the idealized reference itself, right? Where we have the parallel light rays coming in that isn't being diverted by our eyes, and it's only due to the shape of the ground. So anyway, I just wanted to add that on, because we're about to get into different models that are substantiated off of the positions of the stars rather than, I measured the ground and it turns out the ground is actually, a little oblate relative to other parts that are perfectly spherical.
Yeah, isn't it crazy how we neatly tied together the intricacies of Aries' failure and the finer points of cosmography so that you actually can see in real time the absolute absurdity of a globular model that depends on the accuracy of the things that we just destroyed, right? The whole thing about a star being in a perfect position in a telescope in an idealized spot was like, all right, well, actually, with motion, they had to come up with all sorts of crazy explanations. Every glober kind of spirals and comes. I think Franco came up with 7 of his own explanations before going to the relativistic, its own water exists in its own reference frame. Water doesn't actually change the speed of light. Constant is actually varied. It does change, but it doesn't. They go through all that because that position of the star when they're trying to get a zenith measurement is never quite there because they can't quite handle it, right? So that's the backbone of a ground position of a star. So when you're calculating a cosine of an angle and you're getting to a quote zenith, do you know where that zenith actually is? It's like how accurate is that zenith then, right? How accurate is the ground position you're calculating off the thing that you failed to triangulate from a bottom of a triangle that you can't actually complete?
They only need to correct to the idealized version of what they want.
Yeah, exactly. It's so crazy. They went so far and went to the end and it didn't connect. They just looked around and went, "Fuck it, good enough."
Okay, let's correct to it. Let's
Yeah.
make it symmetrical.
Yeah, so actually on that note, there's a book called the Supplemental Nautical Almanac and American Almanac and American Ephemeris, where the British Crown was asked, "Hey, how did you guys come up with these corrections for the Nautical Almanac to derive all these true positions and what have you?" And they were like, "Oh, no worries, bro. We'll put out a publication and explain it all." So they put out this supplemental ephemeris, and it's basically like a history on what I was just laying out about how they'll take a they'll take an elevation angle, and then they'll traverse the land, take a zenny measurement, and then figure out why the two aren't lining up. And that's where they invented the first iteration of deflection of the vertical. The entire book, I think it's in like the first 6 or 8 pages, talks about how all the mechanics in the book are strictly valid for the relativistic concepts and Newtonian, but like obviously they don't use that stuff for cell nav. It's just like they're just like prefacing all that, and then in that preface they're like, and this is all based off of the old deflection of the vertical, and it's like, what's that? And it's like, well, after we cosine, traverse the land, and look up, the star's not where it's supposed to be, so we just assume the ground's not level. So we tilt our device, and then the difference in which we tilt it to make the correction is now how much the Earth deviates from a perfect sphere.
Yep, they're also known as an astrogeodetic deflection or a vertical deflection, right? They do it all the time. They disguise it under different models. How far the gravity direction, remember? Because they defined their other model, the geoid, as a shape that looks like a lumpy ball, but it actually has a requirement that it has to be perpendicular to the vector of gravity, right? So it needs to be that, meaning that it has to maintain to have a down on a geoid, it has to be infinite series of tangents that are perpendicular to the direction of gravity, right? That's the only way they could describe it. And that's how they get deflections of the vertical, because they use that geoidal model and they call it the ellipsoidal model. And when they take your measurements, they can compare these two things together. What they actually do through astrogeodesics is specifically and painstakingly combine those 2 points, right? So when they get to the geodetic, they get the difference between the astronomical latitude and the geodetic latitude. That's the deflection of the vertical. But then what's the purpose of the deflection of the vertical is transformation of astronomical coordinates to geodetic, like we said, conversion of astronomic azimuth to geodetic azimuth, and reduction of vertical and horizontal angles to the spheroid. What it means is you got a point
reduction of the vertical.
Right. You have a point P that exists on, the celestial sphere, and you have a point that exists on the geoid, and you try to mash those 2 points together, and the difference when they don't fit together gets marked as this deflection of the vertical. They call it, it's perpendicular to the gravity vector. They mark it off in their models. They deflect it right away. If we go back to, the father of cartography or geography, Ptolemy, as they say, if you believe in fake Greeks, cited on Wikipedia and backed up by other fake Greeks called Herodotus.
That Ptolemy, you said?
Yeah, I'm sorry. Ptolemy is what I meant.
Thank you,
say.
sir.
I'm not saying it right.
Ptolemy.
So if you go back to, this is the first book ever written about how to make maps, right? And you can notice he's got a pretty well-known projection on the cover. They credit him with it later, and that's pretty funny. But the main takeaway from this book is that his preface, right? And this is just right when it starts, figure 1, the 2-sphere model, right? And it means that to even progress in the book of geography, to even understand how to make maps, you have to accept the 2-sphere model of the cosmos. Well, what is that? Well, it's the geometrical conception of the heavens as an immense sphere, so the celestial sphere, And then with this center occupied by a second sphere, thought of as the Earth, literally describing the celestial sphere and the tangential relationship of an observer to that tangent on that sphere, and that's how the celestial sphere works to a geocentric observer, right? You have a point that's on a sphere of infinite radius that then produces a tangent to another theoretical sphere that is you. And the two-sphere model is the baseline for how to make maps, and that's what we're going to get into with how they're going to measure curvature. Because remember, we have a null hypothesis. We're trying to prove that measurements of geodesy and the Earth can never prove curvature without referencing the stars. And so far, we have a pretty good infrastructure of the combination of the terrestrial and the celestial spheres, as is the name of the chapter in the book, right? Called it the terrestrial and the celestial spheres. And again, the horizon, he's calling the horizon plane, remember, referencing our fundamental plane, to divide the celestial sphere into two equal parts. It's almost exactly the same verbatim word for word of what we said before. When we're going to take measurements to the stars and start making a model based on those measurements called, spherical Earth, or the globe.
Quick question. So the two spheres, the celestial and the terrestrial, since we're transposing positions of stars using a tangent from one to the other, they have to be identical in radius and size?
Well, no. So that's interesting, right? Now, so one is infinite and arbitrary, so you can apply it to anything, anywhere. And the other one has very specific geometric parameters given to us by, quote, geodesy, but in reality, measurements of the sun back from Eratosthenes.
Shout out to Eratosthenes.
Right, because that 3959 measurement only ever comes from a measured circumference, or not even measured, sorry, excuse me, a calculated circumference based off assumed parallel sun rays and angles to the sun, right? So that's how you get a circumference. That's how Eratosthenes did it, based on a known distance between Syene and Alexandria of 800 kilometers, and distance, I think, 7.2 degrees difference. Put that over 360 times 800, I think, gives you 40,000 kilometers, which is, I think, 24,000 miles. So right, so the only calculated dimensions for the globe and globularity comes from assumed measurements of the sun. So again, if we're trying to prove that measuring Earth curve and geodesy comes from measuring the Earth, we've done 0 Earth measurements. We've done 7 sky calculations, 4 laws of cosines, and a bunch of spherical right. So we haven't done any actual measurements of the Earth. And again, our point is that you can make measurements for the globe if you invoke the sky constantly and in perpetuity, right? So here's a little bit more of him going on about how he combined the two spheres. We didn't really need to go into that. I do want to touch on his graticule. He is credited with this graticule. It's amazing how he invented one before longitude and latitude and map projections, before the coordinate system that was using it, technically before longitude and latitude, way before longitude. But we'll ignore all that. Ptolemy was the G. And moving on to how we're gonna. So the other side of the coin here is the celestial sphere, right? And if I always call it cosmography because they're inextricably tied together. Let's start with just a basic star map, right? Looks crazy, like it looks completely different. I don't see outlines of the continents. This isn't quite a Mercator projection. Well, no, it is. It's almost exactly an equal area projection.
Almost exactly, yeah.
Almost exactly, yeah. And if you were to wrap it around, say, an azimuthal, it would look like this, and you can start to see, say, the sun's ecliptic over here, and you can see the Milky Way going over here. You can see the actual. So without any land, without anything, just using the same map projection tools as I would on an actual Mercator, we can use it to a star map, and we can start to get the same shape and overlay. What's up with that? Again, here's an equatorial star map. Here's the Milky Way. We can look at the zodiac in a second. Here's the same projection over here. So when we're saying that we have two models, one of the celestial and one of the terrestrial, if I didn't tell you which one you were looking at right now, you almost wouldn't know. No, we have all the stars. So if we look at them together, typically what you're used to looking at with the globe and the stars all around it with the constellations, same constellations splayed out with the continents drawn on an azimuthal equidistant projection. In the middle, we have the zodiac, right, which is tying it all together. During the typically the daytime, we're looking at the sun and the equinox, and we use this zenith, so we know it's exactly over it in the middle. That's our guideline, and the equator, the terrestrial and the celestial equator, is the big meeting point. It's how we combine and reference both the terrestrial and the celestial. We use the celestial equator is based off of the terrestrial equator, except the terrestrial equator is based off the sun. So none of those equators are based off anything to do with the ground. It's all heavily tied with the sun. And so those two models are inextricably sky models, right? But here's the same data played out over here, and you can see the zodiac in the middle is visible by everyone, always. There's no point on Earth, flat or round, you can be too far north to see, like, not all, you lose some of the zodiac, but you can see at least some of the zodiac anywhere on Earth, even way up here. Well, that I think has different significance. We'll go over that probably in a different presentation. But if you can see the same stars anywhere on Earth, you can start to tell how you can navigate by them if you start to learn them, right? You can start to equate them with stuff. If you know where these stars are and you know their latitude because you know their measurement above the horizon, then the only thing you need to complete the celestial sphere model of this little midground is the time. And that would be right ascension, right? Time, the time it takes for it to rotate around based on the elevation angle it is, gives you, the declination of these stars, meaning as long as you can see these, you can determine where you are on any map, essentially. And that's the basis of celestial navigation on Earth.
Why did they use those specific stars?
Because everyone can see them.
Ah.
Like, it's the only stars that if you live in the south, you can see them. If you live in the north, you can see them. If you live in the equator, they're like equal out, they're,
Exactly.
linearly over you. It's perfect. It's like the perfect guide. So then, if all of this is tied to the sky, and very much we have celestial coordinates and we have angles to stars, the only thing in actuality tying all of these coordinate systems back to the Earth, back to reality, is a datum. Right? And coordinate systems are just number lines Cartesian in space with no real relevance until you forcibly tie them to real world parameters. So we do that with a datum. The most common known survey, right, was the American Arc of the Parallel from way back when, the early 1900s, and they were supposedly measuring the curvature of the Earth. Now, this is we've closed out all the other loopholes, right? All the other ones are definite sky measurements. Can't say they're measuring the Earth from the Earth without looking at the sky and any of the things that we're doing. So it's up to American Arc of the Parallel to save the day and provide the measurements of Earth curve independent of the stars to save the null hypothesis, right? So let's see if they do that. I'll watch a quick video.
Real quick before you do, what exactly is a datum?
So it's it's defined as a thing that would tie a coordinate system to a real world attribute. So WGS 84, NAD 83, those are geodal datums. They are well-known models that they have measured, differentiated, cultivated, and perfected so that they are the models that they have projected to the coordinate system. So those are the datums, right? So that, and how they get those datums is through surveying, and surveying like this American Arc of the Parallel. Yep.
Question. I'm sorry if it's a bad time. I was just going to ask, is there any type of surveying or data points that do not incorporate or that do incorporate Earth curvature so we can go test them?
Are there any datums that include Earth curvature? Was that the
No,
question?
a datum that hasn't been converted to the WGS or you know what she's talking about.
Ooh, great question. No,
Yes.
they don't exist. They are absolutely unicorns. No one's ever seen one. The only datums anyone's allowed to use are spherical. Yeah.
Wait, question though. Follow up. Sorry, Taylor. What about the canal stuff that D3 found?
Yeah. So how they get spherical datums is they get mean sea level averages, and then they just apply geodal corrections based on gravity directions and plumb vertical to wrap it back around the ball to get the differential to the ellipsoid model, right? So you guys are seeing the circle jerk in real time, right?
Let's bend water around a canal to make sure it works.
Literally,
Wow.
they're bending water. You know how we always say there's no bendy water? Joke's on us, boys.
Wow. Okay, all right, we'll get to the canals part at the end, right? I bet. Right, let's watch this.
They've been bending water around us the whole time. Anyway. Yeah, let's see if the surveying can save our non-celestial referencing terrestrial Earth curve measurements.
have somebody come in here and tell me that geodetic surveyors are going out and taking measurements for the geodetic survey goes against everything I've heard.
Yeah, no, that's just what people on the internet chant, right? If you read the actual American Parallel posted on mctune.net/se, it starts with page 44 telling you right away the corrections for this geodesic system for the spherical long lat have already been applied on what you're looking at. So right off the bat, pre-corrected to what? Well, it says for this time, it says on page 18, for the first time, corrections have been introduced for the variations of latitude. So latitude spherical coordinate system induced corrections right off the bat. Again, that's 1897, but the very next page, it goes through tables, right? And it says after rejecting all values that would give purport through a radius greater than 8 inches per mile squared get thrown out. And then it says preliminary latitudes for the whole arc then get thrown out above. So that gives you a range with which they accept, and anything that doesn't match this proposed radius gets thrown out. Unless, of course, you change the whole spheroid model for a smaller radius, and then you do throw it out, and then those two, you throw out the whole next batch. But then you got at page 838, they have astronomic and geodetic amplitude corrections, which is that's an astro-geodetic connection, which means not only are you taking corrections for longitude, latitude, you're correcting them to right ascension declination established in the sky. So you're correcting to both of those right away. And again, that's page 838. That's one of my favorites. 837, right, is when it goes back to say the longitude differences, which are great importance, and that our spheroid doesn't fit the specific curvature arc. And then a spheroid of smaller dimension needs to be called for. So they have to change it up on the fly. Now the radius values will comport. So it's cool. Again, 734. Corrections to latitude, azimuth, and longitude. So these are specific intersection mathematical corrections that use sine, cosine, and let's look at a couple of Greek letters that would just get back to the geodetic. Whenever you're using sine and cosine, you're just comporting back to long lat, which is going to be based on angles to the stars. So again, 734, back to our coordinate system. Can't let it actually get a measurement. 734 just says for this interval, a convenient table is all introduced for the corrections based on the latitudes, based on those intersection formulas from before, something like cosine of A equals y times the sine of A, and then you get all these corrections to get back to the geodetic coordinate system. And then 623, it goes right into the number of star catalogs has been greatly multiplied for the observations and computations for the latitudes. Basically, corrections to all the astronomical measurements greatly multiplied for this specific correction. So all the measurements that they're doing planarly, they're trying to comport with the sphere. You'll notice that the bigger the difference between the points in these triangles, the more curvature they can suddenly manufacture. I mean, quote, find, right? They'll pretend to find it in the calculations as they try to match it to the corrections. The bigger the corrections, the more curvature they find. Coincidentally, they predict they'll find more curvature the bigger they are. Go figure, what do you know? It is true that actually all of geodetic surveying is based on the Earth's dimensions being known beforehand. You cannot compute any of this without an ellipsoid model. If you're measuring a sphere, why do you need a reference ellipsoid? Your Honor, I rest my case. Right, so you don't need a reference ellipsoid model if you're going to keep measuring sphericity. You wouldn't need to keep correcting to the model or have, a threshold of measurements and a threshold of acceptance or any of that. You wouldn't need any of that. So, I mean, I think we would have failed our null hypothesis. We would have failed to provide evidence for terrestrial curvature lacking measurements or references to the celestial. What do you guys think?
Seems like they explicitly reference the stars and positions of them to make their measurements and actually change their measurements to fit the positions of the stars.
I would say they almost only measured the sky when trying to measure the Earth. I didn't see a single Earth measurement in there.
Did someone try to get in and ask a question?
Oh,
Yeah,
yeah.
I was just gonna ask,
ahead.
so if I look at the NG, I'm sorry if I wasn't next,
No, you're
but
good.
I was just gonna ask about, okay, so if I'm referencing the NGS vertical datum, and there's two different data points along the salt flats, and they're 2 inches apart. This data basically shows a variation of 2 inches. So if I go out there and measure that, with a laser test or whatnot, then I should expect actually 32 inches of difference or 34 inches of difference rather than 2 inches. Is that what you're saying?
What? Are you saying that the datums are factoring in curvature? No, they're level, right? Everyone, when they do planar surveying like that, and there's definitely people in here who could answer it more than me, they drop a datum and then they go away and they measure based on that datum. They only ever measure from average sea level or whatever, and then they only ever measure back to like their first measurement. So they're not factoring in curve to those. They're just marking level all the way down, right?
Okay, so they're not okay. Okay, so this is the NGS vertical datum. I guess I need to learn more about how that one in particular works. But I'm trying to use these survey markers and see how much curvature I should expect between them. So are you saying basically I can just use this NGS survey datum, these points to debunk curvature without even doing anything? Because they only measured a variation of 2 inches?
Nope, you confused me. What are you looking at?
I'm so sorry. Okay, so basically, I'm going to try to go out there and survey markers and find these survey markers on the salt flats that run along this railroad. And basically, they say on these survey markers that I looked up online, there's only 2 inches of difference between each of them, and they're every 2 miles. So is there actually 2 inches of difference, or is there 32 inches of difference because there is also curvature they're not accounting for?
Yeah, I don't know. I think so that they marked over how long? 2 miles?
Yeah,
Over 2 miles, yeah.
two
And
inch
there's only
difference.
and
What, plus or minus? You mean?
there's only 2 inches difference between the level on each marker?
Between 2 survey markers over 2 miles.
But 2 inches in what is it? Are you just talking about like an error margin, like a plus or minus?
Yeah, so this is on the NGS vertical datum, and they had 2 different heights, and they were varying of 2 inches of one another. Anyway, I'm sorry, I didn't mean to, like, draw
No,
this
you're
out.
good. Just mathematically speaking, what should you expect off of 1 mile?
Yeah, 8 inches?
Right.
Right. So if they measured only 2 inches between these 2 data points, are
No
they, like
curvature.
okay, so we can just use these data points as they are to debunk the globe?
This is what they'll say. They'll say, well, you can actually fit an immeasurable amount of curvature between each survey marker, right? But if you expand that over a longer distance, then you would get your Earth curve. That's
Well,
what
they
they
were
say.
able to measure a 2-inch difference over 2 miles. So they should
Well,
definitely be able to measure 32
well,
inches.
well, like we were going over, right? They don't measure 2 inches of deviation. They took cosines to stars, got underneath them, took zenith measurements, and then we're off. And the corrections in that area, because it's so obviously flat, they're not going to be able to fit in like full sphericity there. So all they would say is that, oh yeah, it's just a little oblate here, and due to a gravitational anomaly and what have you,
Exactly.
and these offsets, then it's only going to come out in this datum in this localized area as 2 inches per mile squared, and that's all going to be based off of how big the corrections were with respect to the positions of the stars.
Well, so I mean, I think that they only expect about 2 feet over 2 miles anyway, right? Because they do a weird thing where they do so they use, I think, h equals d squared over 2r or something, and then they
Yeah,
go,
you're talking about the parabola versus the
well,
um
yeah, and then so when they do that, it comes out to like 32 inches ish over 2 miles, which is like 2.6 feet, right? So when they say
Yeah.
2 feet, then that's probably what they mean.
So actually, this says the NGS vertical datum does consider curvature of the Earth, and it's
Uh,
established based on geodetic principles.
So yeah, so the geodetic datum takes the planar measurements of the person measuring back from their own measurement, and they put them in the quote previously known dimension models of the model that they're trying to adhere to, with that specific error margin threshold where measurements exceeding or below don't apply, and then they take those measurements and they use the mean and they go, look, we have a model and we've measured to the model. So
Okay,
yeah,
so I should be able to go there and measure 32 inches of curvature between these 2 points.
you'll never do that, but
between
yeah.
2 miles. Yeah, good luck.
No, yeah. You'll never do that. You'll go there and you'll plane survey and you'll get no curvature, and then you'll enter them into the system and you'll apply your corrections and you'll do it and you'll be like, oh poof, look at that, 2 inches,
Yeah, I mean,
There's the
a
2 inches
curvature.
laser.
curvature. I found it. Yeah.
No, with a high-powered laser over 2 miles.
Oh yeah,
No.
yeah. I support your endeavor if you do want to go and do that. Absolutely, it'll just be another point for us. So
So I'm just trying to see what I should expect when I do it. Like, I should expect, only a 2-inch, deviation. Or if I'm going off the globe model, I should expect 32 inches of deviation. Okay,
see,
I get it. I get it. Because they say that they they're going off of geodetic principles, so maybe they're just like nulling out the curvature and just doing like the variations. I don't know. I'm assuming that's what they're doing with this NGS vertical datum surveying. Sorry, Shane.
Possibly, but keep that in the back of your mind as a reference point for you to understand what's coming up next in the Prezi. Because
Got
that
it.
is a good little reference
Perfect.
point to keep.
Perfect segue. Alan's up.
There you go.
Oh shoot! I didn't prepare a single thing. That's unfortunate. 1 second. All right. So
Did
we were
anyone
talking.
else want to get in real quick? I thought there
yeah.
was one more person.
Yeah, absolutely.
This is a
Before we
good
move on.
conversation so far.
And if not, then
I was just going to give a little golf clap, but please continue. This is great.
cool.
Nice.
I have no problem applauding myself. Hold on, I'll do it again.
Thank you, Daniel-san. All right, Alan, take it
Yes.
away.
So I was reading through this old book here, His Pronouncement, which is a great book for celestial navigation and other globular / planar related contentions. And he makes this great point about canals, and this famous one that was made in China or South Korea before they even, you know how they say, oh, we knew the earth was flat or whatever, round in XYZ year. Well, this canal was built before that assumption. And it was like, well, how did they build a curved, ball canal or whatever without accounting for anything like water not being leveled over distances or whatever? And obviously there is no answer to that, but he has a nice little diagram here that I wanted to go over. So this would be like the expected layout for
Alan,
water.
real quick,
Yes.
just want to give people a heads up to get into Alan's stream now.
Oh, good call.
Yeah.
Yeah, we all slid over seamlessly, but in case people weren't following.
Nice.
Yeah, exactly.
Nice. So yeah, they give 3 points here for the water to be curved. One would be like the average. I think that's the C. And then B and D would be the minimum and maximum peaks for tides or whatever. And as you can see here, over the distance of this canal, the water's curved, right? Now, obviously, it's exaggerated for clarity, right? But the fact that this water wouldn't be level or whatever would have to be accounted for and taken into consideration. But as we go through the citations here, in no canal up to and including the Panama Canal were any of these reference to being taken into account for curvature. And he goes through some of the citations and documents here where they were, from people that worked on it. And they were like, yep, no curvature to be seen here. And then he even gets into a citation from the British government where they were giving an order on like the guidelines for how they're going to do, like if you want to do like civil engineering, like build a railway or a canal or turnpike, etc. All these things had to be done in such a way that it was dictated where your horizontal baseline, that fundamental plane, as Shane showed us earlier, has to be consistent throughout the entirety of the project. So they go through that, and there's just no way you have a canal and your royal edict is treated as it's a plane that goes on infinitely until your project's done. But anyway, so the diagram here for for what it would look like on a plane, I mean, it's very simple and straightforward. And then we're going to look at some side view diagrams from actual schematics here provided by our boy Dave. Second. Oh, actually, none of these have an orthographic view, but we'll go for the distance, I guess. Here's I think is this the one in China, Dave? That was built before they knew ball was round? If he's here.
Yep, that's the one.
Yep. Nice. So yeah, they built this entire canal here, treating this like it's flat and there's no convexity to it. They did the whole thing like that. And
No way.
yep.
So they couldn't have done it without geodesy, though, because without knowing previously that the Earth was a globe, they actually wouldn't have known to subtract 2 inches every 2 miles when they were laying these totally level baselines, right? I think
Ooh.
that's how that works.
Yeah, so specifically built before they knew how to do that, and it still works.
Oh man, so then they randomly, haphazardly, just to be lucky, actually already subtracted 2 inches when they were building it by pure happenstance, and that's why it hasn't. I mean, that's why it's fine, right?
Yep. This is why.
Amazing.
See if I can get the name of it. They mentioned
I
it
didn't
here.
realize how well that's tied together, dude. This is great. You didn't give me any context. You just said I'm gonna read about canals. So I was like, I got it. I'm gonna
It's like, yeah, I'm gonna tie.
dude.
I'm gonna tie in
so
canals
excited.
at the end. Well, don't get too excited because this is the peak of it. We've reached peak and now we're declining. So the Chinese Grand Canal, which is the largest in the world, besides which is the Panama Canal. Yeah, so the Chinese Grand Canal there. Then anyway, like I said earlier, the Book of Standing Orders, they give the order that if you're going to be working on a project that's going to be altering the terrain, thou musteth include a horizontal line that covers the entirety of the project. So that's what all of that is all based on. So to tie that together with going back to the old null hypothesis, did these lads build a canal independent of the position of the stars? Well, according to mainstream astronomy and history, yes, they certainly did. And the entire canal works as if the Earth is flat, and then all subsequent canals obviously are said to account for it in some way. But as we just went through that book that has a bunch of citations in it, his pronouncement, you could see where that's not the case. Like they're on the record.
Wait.
Yeah.
Are you saying that water is level?
Yeah, it's kind of hard to imagine that that's possible.
Wow, man, that's crazy. That's mind blowing.
So water on a geoid model is definitely not level, but level is curved. So
Yeah, and level lines mean curved for some reason.
On a geoid model, you just perpetually take tangents to the non-existent perpendicular downward directional relationship to gravity, and in that way, you know that it's curved, right?
Yep.
Dude, we went through all of the magic, the ridiculosity they have to do to,
So crazy
to maintain the model.
The more I hang out with you guys, the more I understand why this is your angle to take, because it's like, oh my, this is the magic trick. This is the entire magic trick.
Dude, I remember early in Flat Earth days when I would be like talking to Ike and ScienceStat and stuff and asking about how the globe model and all that was derived, and it just seemed like so mystical and magical. They're like, look, man, we have parallel light rays that come in. This is the only way you could have a deviation of star positions at 69 miles per degree because of the shape of the Earth, because you can't actually measure like a reciprocal zenith angle at 69 miles away in terms of like physically substantiating that person is tilted away at you by 1 degree. You could only do that with the positions of the stars, and that blew me away. I was like, whoa. Dude, so like it's all based off of that, but then when you get into the specifics, right, the nitty gritty of it, the astrogeodetic surveying and what they do and what the assumptions are, yeah, and Aries and all the information with Starlight and how that works, and it's like, oh my god, you guys just got together, made a dope coordinate system to use a map to traverse the land using cosines and trigonometry for the stars. And then you built a cosmology based off of a coordinate system. And then now you tell everyone like little factoids about how the things in the sky move in relation to the accuracy of your coordinate system that you use for terrestrial navigation.
But first, they were like, "Oh, actually, everyone has to use this coordinate system for all maps forever and always, amen." And then they had to say, "Oh," and then they didn't.
So wait a minute. There was a period of time when lads could freely navigate anywhere without using reference to a longitude.
Yeah. So I mean, historically, up to like 1714, everyone could navigate without the concept of longitude. There was no unified, so-called global coordinate system. People were just looking at the stars, dead reckoning. They were figuring out time based on, Jupiter's moon, transits, other celestial phenomenon, timed eclipse cycles, all sorts of cool stuff. And then all of a sudden, the Royal Society was like, hold up, wait, nobody can navigate because we need to have longitude. And if we need to have longitude, we have to send people down as far south as we can go so we can take celestial observations, so we can finish push the final touches on this model so that we can mandate the coordinate system. That's the order of events, I think. But, prior to that, everyone was cool. People would sail in all over the world for at least, thousands of years when no one had invented longitude. Apparently, the people who invented longitude, the Greeks, right, were in BC time, so that's 2,000 years before the Royal Society decreed that they needed it. They had invented it in caves. They invented their own method. If we go back to Ptolemy, in his book on Geographia, he has in it longitude and latitude. Not so much. He has it in terms of stadia, right? Defined local longitude term. Literally has GPS coordinates in a system that didn't exist yet, all through his book for all the important landmarks of the world. So if you believe Wikipedia, longitude and latitude was invented and then left forgotten kindly until we needed it 2,000 years later in 1714.
I have
Anyway.
a quick question, if
Wow.
that's all right.
Absolutely, Gally. As long as it's a hard-hitting question.
You make it
It's pretty
slow.
good. So in that book that you pulled up, that I think it was the first page, it said 1922, where it says like we have to accept the rotundity of the Earth. Why in 1922, was it even a question whether or not it was flat or rotund if it was decided 2,000 years ago? Because it seems to be up for speculation at that point. It doesn't seem to be like it's been decided for 2,000 years, right? It says like, thus this is why we cannot accept the Earth is flat, right? Like it seems like to be still a debate in 1922, right?
I know that in all the books in the late 1800s and early 1900s, they are combating globularity as if it's new, and that the defining prevailing common sense theory is that, of course, it's flat and level and stationary. And the people who say it's not are retarded. That is literally what they say, and not so many words from their own perspective. Like if you read Gleason's book, "Is the Earth a Globe? Is the Bible from Heaven?" It's from the perspective of him trying to convince his dear friend, I forget his name, Dimbleby. That's a goofy name, right? His Glober friend Dimbleby. He's like, listen, bro, it's definitely flat. And Dimbleby's like a chronographer who thinks it's a globe. And the whole book that Gleason wrote was all the evidences of why it's flat and how it's flat, right? And how it's level. And his whole attitude is, there's a bunch of people saying it's round, and they convinced my buddy, and I want to save him from the round cult. And that's why he wrote a book, right? And that's the whole perspective. But so it's almost like everybody knew at that time that people were pressing something new and they were resisting. And now when we look back, they were like, nope, nobody ever resisted. It's always been a globe. Everyone's always known. It is known. It is known. And they start rocking back and forth.
His globe. I
Yeah.
think
His
perhaps
globe. His
circular
globe.
reasoning is not adequate enough. We cannot call it circular reasoning. We're gonna have to start referring to it as globular reasoning. We're taking it a little further.
I like what
I
you're
have
saying.
a good working
Perennial
hypothesis.
problem.
Daniel, you're killing us. Are you trying to speak?
Nah, his kids are playing in the background, I
sorry.
think.
But thanks for answering that, Shane. I didn't know that it was still up for debate if it was settled 2,000 years ago. It seems like those two things can't be both true at the same time.
Yeah,
I got
well,
a
it's
really
funny you mentioned that. 'Cause I got a book from the 1920s as well called The Enlightenment of the World. And it's this professor, and he's writing, I think he was a professor. Anyway, he starts writing about some different flat earth arguments, and people were writing him, and they were like, dude, thanks. The only reason I believed in the globe is because men of repute were telling me that it was a globe, but like they didn't really give me any reason to think like strongly otherwise. So like, yeah, I think they just kind of like imposed it, and then they were like, this is what it is now. And everyone was like, is it though? And then after like a couple of generations, it became the inverse.
Yeah, I think it's the two to three generation rule where they took over the world and changed everyone's hearts and minds.
Generations, baby. Yep.
But I'm pretty sure that my working theory is like right around 1890 to like 1920, they were inserting the globe, and they were also rewriting history, and they were recontextualizing previously known history in the favor of globularity, right? That's
And
because
creating
all
central banks and
yeah,
World War
all
One and
also yeah, absolutely.
yeah.
But they were laying the groundwork for the what then became the Wikipedia-backed historical record of globularity, right? You got, oh well, we've known for thousands of years, based on people like Eratosthenes, based on people like Ptolemy, based on people like Hipparchus, who they had said invented longitude, right? They just list all these fake Greeks, and then they're like, oh, this other fake Greek, Herodotus, the father of history, actually cited all these people, and that's how. So all the fake Greeks corroborate each other. Like, what kind of evidence or record is that? Like, the Wikipedia says so. It's what it amounts to, and it's crazy. So all they had to do was invent a couple of pages of Wikipedia about sticks and shadows, and boom, they can recontextualize history and then invent, the history of what we do. It's always been known. All of a sudden, it's always been known.
So what you're telling me is the only way out is to just start writing our own history and going like, yeah, it was always flat. We've always known it's a flat. A couple of globularists came around measuring shadows, talking about how they measured the circumference of this place, but it turns out that's just the radius of your vision.
Well, honestly, dude, when they start lying about history and time, what you got to do is study the sky clock, learn about eclipses, unwind the eclipse cycles, figure out what the great astronomical year is, do a couple of rotations of 18 years, 10 months, 11 days, 8 hours, so you get 651 years, wind that clock back, and then use that as a chronometer to analyze historical records, like our boy did. The what is he? I almost said a chronomancer, but that's definitely not what he is. He's a chronographer.
I mean, but henceforth, obviously,
He's a
we're calling it a
We're
chronomancer.
doing chronomancer now,
Yeah.
for
It's a
sure.
professional title of chronographer, I think. He wrote like 5 books, and he went through the historical record through the lens of the chronometer of the eclipse clock, right? So when you backtrack the cycles of the sky, that's how you unwind the lies about time. That's just what I think.
Real quick, gents. There's quite a few people in here. I just want to make sure if anyone has any questions or want to bring up another point that was part of the Prezi. Anybody, don't be afraid.
Filibuster.
Mute him.
And if not, no worries. We'll probably be discussing this anyway to continue them.
Yep.
Yeah, and also there's to support the theory that it was a recent deception. Here's a bunch of newspaper clippings from like the 1900s. It goes like 4,000 of them from 1860 to 1960 about mentioning flat Earth, flat this, flat tests, radio wave, all sorts of stuff. A couple entries about Zion. It's a little bit odd, but yeah, I mean that also supports the theory that 100 or so years ago, most everyone knew the Earth was flat.
But wouldn't they all have to be in on it?
Why the lie? Why? Why would they do it?
Why the lie?
If anyone has seen Europa, right, and familiar with the Bolshevik Revolution,
Never met her. Not familiar with any revolutions.
I got like 8 hours in there. I got 4 more to go.
About how a certain group of people with say money can infiltrate subvert a whole government really quickly, relatively, to be towards a universal goal, right? It's pretty easy. Happens all the time. It's also known as communism.
Touche. All right. Anyway. Well, with that said, I think we'll wind it down. And like Beast was saying, if anyone has any questions, we're open.
On a side note, I streamed my whole stream with myself on mute, and since I did most of the talking, this whole thing has been a bust. My fault, everyone.
Oh. Dude, rip. That's really funny because I did my whole stream under the Flat Earth Friday restream title. So.
Yeah, I saw that, but it seems solid though. It seems fine.
That's so annoying.
These Prezzies are best in person anyway. Just a fact.
Yeah.
Is anybody recording on Discord?
Yeah, of course.
Yeah, we both were, but
new perspective.
But only one of us was doing it really good.
Okay. I'm so sorry.
You're good.
I thought it was a really cool presentation style, how you guys kind of double teamed it, like you kept passing the baton. But that was really neat.
Little good cop, bad cop.
Little good cop. That's what me and Luke are doing.
It's funny because we kind of figured out the stuff by independently looking into whatever we wanted, and then we were comparing notes one day,
dude, yep.
Gravity vector lines of how? Wait, satellites need what? Well, how come that doesn't affect the survey on the ground with their geopotential vector? And I'm like, what? No, that's weird.
Oh, dude, that was such a good one. Dude, let's take a gander at that really quickly because that was one of the. I don't know. I just like that one a lot.
And it still continues For example, D3 with the canals, bro. It's
Yep,
like
another sweet gravy data point.
absolutely.
Yep.
Yeah, I agree. These partnerships are great. You guys should do more partnerships.
More duo prezzies.
Well, this was born out of laziness, so that very well could be
But it's
Duo
so
prezzies.
succinct.
How about
it's so-
lazy prezzies?
I threw this together like 20 minutes before here when I can't get home from work today.
All right. So earlier we were talking about the geoid model and astronomical deflections of the vertical due to gravitational potential offsets. In the diagram that Shane was showing earlier, you saw a plug bob not going straight down, meaning that it isn't going to the center of the ball. Now, in reality, the plug bob is definitely going straight down, and you can use spirit levels to determine, that the device is actually leveled or whatever, right? But the star that they're referencing for the correctness of the positioning of level is not where it's supposed to be. So they say, okay, well, maybe there's a gravitational anomaly here, and the way that it would normally be where down would be down towards the center of the ball, this is actually offset, and there's like a physical deviation caused by this gravitational potential such that my plug bob isn't going directly down. It's an illusion. It just looks like that. And I know it's not real because when I look at the star, it's not in the center. So the only thing that could be true is that there's a correction that's even different from the oblateness of the Earth, right? Where like it could be a shape dependent correction. This is a gravitational potential correction based on the correctness of the area. Now they don't get out the gravitometers or start taking gravity measurements and timing or anything like that to calculate the offsets or gradient potential changes or anything like that. There's a change in the gradient here. Does that mean 9.8 meters per second squared is different here? Nope. No one's ever really confirmed that. Well, but what we do have, right? So think about this, right? They said that they have a physical object that's hanging from a telescope or theodolite, and due to the gravity difference, it's changed its actual location in reality. Okay, cool. Now, if that's the case, if you send an electromagnetic signal somewhere in that area, the density gradient, the strength of that gravitational potential, is going to cause a frequency shift in that light. Which is gonna cause a timing offset, and it's gonna require corrections because GPS is a timing interval system based off of a fixed speed of light. So when you have that value, the measurements in between how long this, or from when the signal was sent to when it was received, that timing difference is what you're getting distances from. So if you're sending a signal into a location that has a different gravitational gradient, it's going to affect the timing of that signal when it gets received to the receiver because the frequency is going to be altered. And it's going to change the distance. It's going to lead to inaccuracies. So let's assume for a second that the geodetic surveying, when they did the arc of the parallel, and is correct in that there is a gravitational potential correction needed. Then in GPS, what would have to follow is when a signal is being sent to an observer at whatever the location is, there would have to be additional corrections made in that for that area to account for the localized offset due to the gravitational potential changing the frequency of light. Now we know from the experiment in the 1960s, pound Rebka, pound Snyder, even at an altitude of 75 feet above the ground, there's a frequency shift that's measurable and detectable. So for highly precise distance deriving positions based off of timing and the analysis of the frequency to derive all that from the encoding, you would have to have some corrections for this. This would have to be substantiated in GPS, and especially in the south where we get into Australia, where they have 30 arc second corrections due to gravitational potentials and deflections of the vertical for oblateness. So if that were the case, where these things existed, then you would have to have corrections for them, yet none of them exist. So when it comes down to it, a satellite makes the same gravitational potential corrections uniformly, because that's the other thing that they say too, is that they say that due to the Earth being an oblate spheroid and rotating through a fixed gravitational field, all potential gravitational offsets are naturally work themselves out due to the unevenness of the shape of the Earth rotating through a uniformly distributed gravitational field, and it just magically works itself out. So they actually use a uniform gravitational potential correction at the altitude that they say they're at. So at an altitude of, they say at 20,000 kilometers. So imagine there's a satellite up here, ball here, you're sending signals to people based on their location. There's going to be a gravitational potential correction if they existed in the way that they were derived and asserted from geodetic surveying. But as I stated, no corrections are needed, and they actually use a uniform correction for everything, such that it would be equivalent to the satellite flying over a plane, due to whatever orbital mechanism it has. So it's just completing a circuit in the sky, and the ground is always at an equidistant altitude from under it, and there's no differences due to elevation or gravitational potential.
Dude, it's almost like you have one completely uniform sphere, and that's the gravitational effect applied to satellites, uniform across the board, a single color. And then you have the geoidal lumpy ass model with the Australian defects and the 1,200 papers about how no one can drop a plumb up this level due to all the gravitational influences of the weird anomalies in that one continent. But the satellites, are all fine. I feel like there's a large discrepancy in the when you have made up gravitational anomalies so close to each other,
Huge discrepancy, bro. If the frequency shift on that signal is changed outside of its established parameters for reception, then the timing is going to be off, which means the accuracy is going to be off, and it's going to be useless. So if you have a strength potential that's physically causing an object to not be going down to the center of the ball, then it's definitely going to change the frequency shift in light, if even doing it in a place where it is equipotential, just changing an altitude from 75 feet to 0, has an effect.
It's crazy. When you keep using the same lie for different things, then stuff like this starts to come up.
Yep.
And stuff like this starts to not make sense.
It's like, okay, why isn't my plumb bob that's on the rotating sphere rotating through the equipotential gravitational field that's fixed? Why isn't that offset such that my plumb bob doesn't require any corrections? That's completely contradictory to the two fields of study, GPS and surveying. Yet they're both intertwined and require the same lie to substantiate one another, even though it contradicts.
Why? Why?
Why would they do this?
Why would they do this?
And then how many interconnecting layers of this hold up the globe? And it's almost insurmountable, right?
Yeah. It gets to a point where it's like, oh, I see what you did there. You use the one thing you assume to reify the other to on the back end talk about how that proves the thing you first asserted. Nice.
Yeah, dude, muons, fake particles, everything that they've come up with, so they can just make shit up. It's dark matter. Doesn't matter, doesn't work. It's not like we'll just fix our theory. We'll just throw a mathematical overlay over everything each time.
So have you heard of dark curvature?
Sorry.
So there's this idea, Shane, that there's this curvature out there terrestrially, but for whatever reason, it doesn't interact with the electromagnetic spectrum. And it can't be observed in any meaningful way. And actually, things that are on the other side of the dark curve get refracted around it, such that it makes it look like there is no dark curve, and it's just a plane that you can just see at different distances on throughout the day due to varying conditions.
Yeah, and you can treat it as such when you're flying over it, according to our friend Dave.
Well, yeah, because it doesn't interact with matter either, so
it's
not going to affect the plane.
On it, up to 600 miles, but when you start measuring stuff, or when you start looking through a theodolite, all of a sudden it's curvature. Building bridges, don't need it. Building canals, never heard of it. But theodolite, boom, there it is.
Never heard of it.
Found it.
Well, if you look in the distance, you'll see that it shows a concavity.
Very nice.
All right, Shane, I just wanted to tell you one of my favorite parts was seeing the source sun from above and then the side angle to show it lifting and dropping in the analemma. I think that was a really key visual for people trying to understand like what the sun does and kind of how it appears to us. So thanks for all the visuals with the Azimuthyl Grid of Vision. You guys are legends.
Thank you, Mr. President.
You're a
You're
legend
amazing.
too, JTZ. That was our president, Run Boston Bear, president of Flat Earth. Liliana, if you want to read us a coffee ad on the way out, that would be fantastic. And I need to remind you, you are contractually obligated. So if you try to get out of it, you will be sued.
After that ad, I would also like to read an ad, please.
We'll see if there's time.
Is it time for the testimonial already?
Absolutely, Lily.
Oh, well, the ongoing saga with these aliens regarding brushtail coffee. Yeah, I have to tell you guys. So I told you those ETs, the ones that abducted me, the good ones. They're nice ones. They're small grays and they're pretty nice. All they want is the brushtail coffee, and they truly believe that I manufacture it in my kitchen, which is why they abducted me to try and get me to make it for them in their kitchen. And they drink thimblefuls of this brushtail coffee and they just love it. Anyways, long story short, word has been getting around to a bunch of these alien ET people, these humanoids, and they're all getting turned on to brushtail coffee because it just makes them like the most comical, pleasant, happy drunks. It's kind of funny to watch them just be so silly. Anyways, long story short, now there's a bunch of other ETs that have found out, and one of them who I befriended told me that the bad guys who control us, I won't name them because they didn't name them to me, so I don't know, but they just referred to them as bad guys in our country. And so they said the bad guys in our country are planning on getting some ETs to come and invade us. And they said, you know what? The only way you can defeat these ETs is just offer them some brushtail coffee. So, folks, just arm yourself with some brushtail coffee, and the incoming ET, what do you say, like conquest, or at least attempted conquest, we won't be defeated. Yeah, they're coming for us because the bad guys in our government supposedly are letting them come in and take over or try to take over. But the only way we can defeat them is with brush tail coffee. And plus, it's delicious. So I think it's a win-win for everybody. Stock up on your brush tail coffee, people.
It's a tried and true method for fighting off any type of bad guys that don't have names, but it's been done since the Bone War of '05. Could I do a quick ad about a friend of mine? That'd be all right.
Absolutely, absolutely. But before we get to
Alright, so
that,
there
Lily, thank you for defending us against the impending invasion and serving as an ambassador in making coffee for the ETs. Much appreciated.
Well, we have to thank Brushtail Coffee because they are going to save the day.
Oh, no, 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 no. We're thanking you specifically because then they're going to start kidnapping Toby. It's better that they think it's coming from you and you're the source of it. That way you have all the power and you can negotiate.
I will deflect them. I will keep telling them that I make it in my kitchen, but I'll just keep demanding for more, protection and rights and stuff for us. Don't worry.
You know that magic trick you do to children when you're like, "What's that behind your ear, lad?" And you pull a quarter out, but you were holding the quarter the whole time?
Right.
I need you to do that to the ETs with a cup of coffee.
Yep, you got it.
All right, Gally, you're up next.
Yes. I just want to tell you guys a quick story about a young man. Well, he's not a young man anymore. He's a man, but he was a young man from Texas, and he had a dream to run an Antarctic marathon. And I really want to get him there. So if you guys keep in the loop, I have a friend named Run Boston Bear who is in the future going to be looking to doing the Antarctic marathon and possibly coming up soon. He may be, it may be very helpful for him to get some donations to get that going, and we can see JT on ice, and it would be really nice to have that happening. Just wanted to put that out there for now.
Well, that
Hey,
Oh,
bro.
JT on
I
ice. That's it.
I will donate for sure. I will donate. And folks, I want to, while I'm here, I want to encourage you guys to also subscribe to all the teachers. Thank you.
Hey, thanks for the ad. Yeah, I'm pretty excited just with everything that's been going on with this whole deal to go down there to the exact spot. It's a 10K course that you just lap. And if anybody hasn't looked at the 2024 Antarctic Ice Marathon footage on their Instagram page, it's amazing. Totally calm. It was the day before TFE showed up. You don't see any footprints and you don't see any breaths, which is really interesting. And I want to go be a part of this wild, uh, environment. And I'll try to get top 3 for you. So just be looking out for a fundraising effort from the community. And I talked to Flat Earth Dave about it, and I'm probably going to wear a Flat Earth shirt over my jacket and run as hard as I can. So thank y'all for the support whenever you see that fundraising page.
Nice. Looking forward to it.
Excellent. Cool. Close out.
That was a great stream, man.
All right, lads and ladettes, we're going to wrap up. See you guys on Friday for Flat Earth Fridays. And actually, there might be a debate this week with our boy Dom and Mordwand, but that had to be rescheduled. So we'll see if that comes into fruition later in the week or next week or what have you. But anyway, see you on Friday, lads.
Hey, I was trying to retweet, but I didn't find your tweet.